about Distillation, a big teacher model, a smaller student model, and the dark knowledge in those teacher outputs that helps the student learn better. The real question is, how do you use your compute budget wisely? Should you invest in a bigger teacher or bigger student? And when does Distillation actually outperform supervised learning? Well, it turns out that there's a sweet spot. Sometimes the student even outperforms its teacher. But if the teacher's too powerful, the student can't keep up. That's the capacity gap. This paper dives into the math behind it all, running experiments on models up to 12.6 billion parameters and data sets with 500 billion tokens. They came up with a scaling law to predict how well the student will do based on the teacher size, the student size, and how many tokens they train on. So, when should you use Distillation? If you've got a pre-trained teacher or plan on distilling multiple students, it's often a win. But if you're starting from scratch for just one student, supervised learning might be better. Ready? Let's dive in.
Let's start by looking at the broad idea behind distillation in machine learning. Distillation is a technique where a large teacher model transfers its knowledge to a smaller student model. Essentially, the teacher's output probabilities for each token or class serve as a rich learning signal for the student. Instead of simply learning from the correct label or next token, the student also sees how the teacher allocates probability across all possibilities, sometimes called dark knowledge. This extra information can help the student model learn faster or achieve better accuracy than it would through standard supervised learning. In this paper, we have a distillation scaling law, which is basically a way to predict how well the student can perform given a fixed compute budget, depending on how we split that budget between training the teacher and training the student. The key question is how best to juggle compute resources to get the strongest possible student model. Why is this important? Well, if we need to distill a lot of students, or if we already have a pre-trained teacher model, then distillation ends up outperforming traditional supervised learning, but only up to a certain compute level. On the other hand, if we have to train the teacher from scratch for just a single student, it's typically better to do supervised learning directly. We've seen from existing scaling laws and language modeling that balancing model size and training tokens leads to great performance. That works nicely, but inference costs keep going up with model size, and that makes deploying these massive models tricky. One workaround is overtraining models, pushing training beyond the usual stopping point to gain efficiency in the long run. Take a look at the key figure here, which shows the relationship between the student's loss and the teacher's loss. Notice how under certain conditions, the student can beat the teacher? The figure also illustrates how changing the student size and token budget impacts distillation efficiency. Bigger students plus more distillation tokens often lead to lower loss, though it depends on the total compute you can spend. This sets the stage. We want to find the best way to scale distillation so that smaller models can inherit knowledge from bigger models without blowing our compute budget. Now, let's dive deeper into why this topic matters. Training huge models is expensive, and running them in production can be even pricier. Distillation is one of the most common tricks to reduce those costs while keeping performance high. In a nutshell, a bigger teacher model passes down its knowledge to a smaller student by sharing its output probabilities, often called dark knowledge. Some researchers argue that dark knowledge helps students learn more efficiently because it reveals richer information in the teacher's probability outputs. Others say it acts like a regularizer, removing noise and stabilizing training. Whatever the reason, major projects like Gemini and Minotaur have successfully used distillation, but there's a catch. Sometimes, supervised learning can still outperform distillation, depending on how each is done. So how do we know when distillation is truly helpful? Stents. That's where the distillation scaling law enters the picture. The authors ran large-scale experiments on models ranging from 143 million parameters up to 12.6 billion. Training them on datasets as big as 512 billion tokens. The results show that the student model's performance relies on three main factors: the student's size, the teacher's size, and the number of training tokens. Turns out, it follows a power law pattern, meaning performance evolves in a predictable way as we scale up compute. A surprising twist is the capacity gap. If the teacher is too strong, the student sometimes struggles to catch up, and that can hurt final performance. The authors confirm that distillation only comes out on top if the teacher is used efficiently and you allocate compute wisely. In other words, distillation can be great, but it's not a universal hack. The rest of the paper focuses on exactly how to get it right. Let's talk about a big question in model training. How do we balance model size and training data while also keeping an eye on compute costs? Some folks aim for what's called compute optimal models. These are models that deliver the best performance possible given a fixed compute budget. Typically, these models use a fixed ratio of training data to parameters, but that might not always be ideal. Researchers get around this by trying two main strategies. One is to hold the model size fixed but vary the training data. The other is to adjust both model size and training data while holding total compute constant. These approaches help us see how performance scales in different setups. Another crucial element is how we measure the student's distillation loss. Storines. Normally, language models do next token prediction. They guess the next word, and we measure how close they are to the true next word. In distillation, however, the student also learns from the teacher's probability distribution over possible next words. We often use KL divergence, which measures how one probability distribution differs from another. We might add a temperature to smooth the teacher's probabilities, making them easier for the student to absorb. Finally, these different parts, next token prediction loss, distillation loss, maybe some stability loss, are combined into a single training objective. That's the core formula the paper then uses to propose its scaling law, which helps us figure out the best compute allocation for distillation. At this point, we know scaling laws are central to understanding modern ML. Now let's see how they apply to distillation. The distillation scaling laws predict student performance based on teacher size, student size, and how many tokens the student sees during training. To get accurate scaling laws, the authors carefully control their experiments. They use student models ranging from 143 million up to 12.6 billion parameters, along with a variety of teacher models, both larger and smaller than the student. They also train the teacher on a different data split from the student to make sure the setup is fair. One concept highlighted here is the fixed M teacher/student isoflop approach. The name might sound fancy, but the idea is that training a student on teacher outputs can mirror training the student directly on the data, which allows power law scaling to hold. But teacher-student generalization isn't guaranteed to be perfect. Sometimes the student can outperform the teacher. This is called weak to strong generalization. If you look at figure 2 here, you'll see how different teacher sizes affect student performance. It plots cross-entropy loss for students trained with various teachers, showing how both teacher size and compute allocation shape the results. They then introduce the isoflop teacher/fixed M student approach to dissect how teacher size and training tokens each contribute to student cross-entropy, because the earlier approach couldn't isolate those two factors. By focusing on controlling teacher resources and keeping student size fixed, they can refine their scaling law predictions. So how do teacher size, student size, and training tokens all come together? That's the question tackled next. First, we have the isoflop teacher/fixed M student setup, where the student size stays constant, but the teacher is trained under different compute budgets. Check out figure 3 to see how the student's cross-entropy changes based on different teacher performances. Then, they examine fixed M teachers/fixed M students, where both teacher and student sizes remain fixed, but the number of training tokens can vary. Figure 4 shows that making the teacher better doesn't always boost the student's performance. This is the capacity gap. If the teacher is too far ahead, the student can't generalize the same way, and it ends up underperforming. To make sense of these observations, the paper presents a distillation scaling law, a formula that predicts student cross-entropy based on teacher cross-entropy and other scaling variables. It fits a broken power law pattern, meaning performance behaves differently depending on whether the teacher is stronger or weaker than the student. 3 big conclusions pop out. If the student had infinite capacity, it would match the teacher exactly. A random teacher leads to random student performance, regardless of student size. An overly strong teacher can actually hurt the student's final performance. This law captures why distillation can sometimes fail, and also how to tune it for better results. But how well does this theoretical law match actual data? This section addresses that. If you look at figure 5, you'll see how both the supervised scaling law and the new distillation scaling law compare to real-world model performance. The match is quite tight, within about 1% error. So these equations do a good job of describing what really happens when you scale up or down. Next, check out Table 2 to see different ways to account for compute when doing distillation. In the ideal scenario, the teacher's compute cost is completely amortized, meaning we only worry about the student's training cost. But in more realistic cases, we might have to count teacher inference time, or the cost of training the teacher from scratch. All these details shift whether distillation is practical for your budget. Then there's the matter of total floating point operations, or flops. We'll call them flops from here on out. The paper introduces an equation for how to tally up the flops needed for the whole distillation process, covering student training, teacher inference, and teacher pre-training. One subtlety is that standard flop estimates assume all parameters matter equally, which isn't true when context sizes get huge. A correction factor is added to improve accuracy. At the end, the authors raise a question. When does distillation actually beat supervised learning? If loads of compute or tokens, supervised learning tends to win. But if tokens are limited, distillation could be a good path. Now, which teacher is best? Generally, bigger teachers give smaller cross-entropy, which is good for the student. But the larger the teacher, the more you spend on compute. There's always that trade-off. The paper suggests that if you're on a fixed compute budget, the teacher's cross-entropy should go down as a power law as the student's size grows. That means bigger students benefit from teachers that are more accurate, i.e., have lower cross-entropy. But there's a tipping point after which pumping more compute into the teacher just isn't as worthwhile. Interestingly, it turns out teacher and student scales often track each other linearly. Look at Figure 6 to see how teacher size and student token budgets interact. Blue areas in the diagram mean distillation outperforms supervised learning. Red areas mean the opposite. White dashed lines show different teacher sizes, so you can spot the teacher's impact more easily. Figure 7 continues this idea by plotting the student's cross-entropy for varying teacher-student token setups. The red line indicates the best teacher at each combination, highlighting an optimal distillation strategy. Finally, the paper outlines a compute optimal distillation formula. It's an optimization routine that picks the best teacher and student parameter sizes for a given compute budget. If you let the budget run high enough, supervised learning generally beats distillation. But for smaller models or constrained compute, distillation might be the winner. Here's the concluding punchline. If you want the best possible model of a particular size and you don't already have a teacher, supervised learning is your go-to. When you factor in the cost of training the teacher, distillation can't beat supervised learning in terms of raw cross-entropy. However, if you plan to distill multiple times, or you'll keep using the teacher for a bunch of students, then distillation could be more cost-effective. Figure 8 shows different training scenarios. Notice how supervised learning comes out on top when all compute costs, including teacher plus student, are counted. But for server setups, where a single teacher is used repeatedly, distillation can come out ahead on compute costs over the long haul. In Figure 9, you'll see how teacher size scales as compute goes up. Initially, scaling up the teacher really helps the student, but at some point, bigger teachers don't offer as much benefit compared to simply increasing the student's training tokens. That's because inference with a very large teacher is expensive, and distributing compute elsewhere can be more efficient. Finally, check out Table 3 for a quick summary of the best ways to use compute at different model scales. For small models, pour most of your compute into training the teacher. For mid-sized models, split the budget more evenly. For very large models, a balanced approach is recommended. So the paper closes by underlining two situations where distillation is especially worthwhile. First, when compute is on the lower side. Second, when a teacher model is already in hand. The distillation scaling law they've introduced serves as a guide for reducing inference costs and improving efficiency at test time. Thanks for joining us today. Happy learning and stretching together.